Hi, this is Professor Stuckard, and in this video, we're going to be discussing the cross product. So what is the cross product? Well, if we're giving two vectors in three-dimensional space, then the cross product of those two vectors is going to be a third vector that is orthogonal or perpendicular to, well, the two vectors that we're given. Now, we do have some restrictions or properties of this cross product besides it being orthogonal. First, it has to be oriented according to the right-hand rule, which we'll talk about in a second. And the magnitude of the vector created by the cross product is going to be equal to the area of the parallelogram spanned by the original vectors A and B. So again, we're going to be building more parallelograms based on vectors as well. The notation for our cross product is, well, A cross B. And we use the old times symbol that we used way back in elementary school when learning our times tables to denote the cross product. So we need to be very, very careful here when we're talking about different types of products, especially involving our vectors. We need to make sure that we're using the proper notation. If it's the dot product, well, we need the dot. If it's the cross product, we need the cross. And if it's just scalar multiplication, we typically don't put any symbol. Another important thing to notice is, of course, that the cross product results in a vector. So when I do the cross product, my result is a vector, which is different than when we did the dot product, because when we take the dot product of two vectors, that result was just a scalar quantity. So where does this concept of the cross product come from? So the idea is that if I'm given two vectors in space, and you can actually do this yourself. If you hold two pencils up in the air with their tips together, which would be kind of like standard position, you will absolutely be able to find a plane on which they lie, which means if you have those two pencils up in the air, you should be able to find a book or a folder or something so that both of those lay right on there. So let's kind of take a look again. So if I have two vectors in space, in this case A and B, I'm going to be able to find a plane that they both lie on. Right? There's definitely that plane that they lie in. Then the cross product is orthogonal or perpendicular to that plane, meaning it's going to stick straight up. So if you had like a piece of paper on your desk and that's your plane, the cross product sticks straight up out of that piece of paper. And that's what the cross product is. Now that right-hand rule. So the way the right-hand rule works, that tells you which direction your cross product is going to face. So with the right-hand rule, the first vector in the cross product becomes your index finger. The second one is your middle finger that you curl inward. So with your right hand, you would curl it in, and then your thumb is going to point in the direction of that cross product, straight up, which means that the order is going to matter when we do our cross products. So how do we calculate the cross product? Well, if I have vectors A and B, and the cross product of A and B is some vector C, I can actually set this up as a system of equations to solve, because I know that if my cross product is orthogonal by the dot product theorem, A dot C and B dot C must be 0. And I can actually set up this system of equations to solve. And I can actually go ahead and solve them for C1, C2, and C3. Now, you can absolutely memorize this definition. That's fine. It's all just algebra anyway. However, that's typically not how we calculate cross products in practice. Typically, to calculate a cross product, we use what's called a determinant. So, a determinant is a feature of square matrices, and we'll start with a 2 by 2. So the determinant of a 2 by 2 matrix is given by multiplying basically the corners. So in this case, A times D, and then multiplying the other corner, B times C, and finding their difference, subtracting the two of them. And that's how we calculate the determinant of a 2 by 2 matrix. if we're doing a larger square matrix, we do what's called minor matrix determinants. So how would that work? Well, we're going to set up the determinant of a 3 by 3 matrix. And the way we set this up to find the cross product of vectors A and B, the top row is always your standard basis, ijk. Then the next row is always your first vector, so in this case A, which is 1, 1, 3, 4. And then the last row is vector B, which in this case is just going to be the components 2, 7, -5. So again, we're setting up our standard basis, then the first vector, then the second vector. And the way the minor matrix determinants work is we're basically going to go through this matrix and find 3 different 2 by 2 determinants. And so we'll start with the first one. So to find the I component of the cross product, we basically circle I and then cross out the row and the columns associated. And then we can see that when I cross that out, I'm just left with now a 2 by 2 matrix. And if I find the determinant of that 2 by 2 matrix and multiply it by I, well, that's really giving me my I component. So now I have my 2 by 2 matrix and I do my determinant following that, well, determinant rule, right? Multiplying the corners, so 3 times -5, 4 times 7, and taking their difference. And so -15 minus 28 is really -43. And so my I component is -43. Now we'll do the same thing for the other components. However, we want to be very, very careful. Each time we do a new 2 by 2 determinant, we need to change signs, which means when we do the J component here, and again, same idea, circle J and then cross out the row and the column that's associated with J, and we turn that into our minor matrix where I can find that 2 by 2 determinant. And again, see, it's 1, 4, 2, -5, those are the leftover values. And again, we're going to do that determinant. So we multiply across, 1 times -5, 4 times 2, find their difference. And again, don't forget about that minus sign. Every time we do the J component, there's going to be that minus sign. So anyway, we have the minus, and then it's going to be -5 minus 8. So when we simplify all of that, we end up just getting +13 for my J component. All right, so again, be careful, work slow. You don't want to lose negative signs here, and it's very easy as these things start getting, well, a little bit more complicated. So again, just take your time and work through the process. Last up, K. So doing the K component, again, circle K, then cross out the row and the column associated with it. Leaves us with our 2 by 2 matrix, 1, 3, 2, 7. And again, that'll be in the K component. We're changing signs again, so this one is positive, which means you don't have to worry about putting a negative sign. And then again, 1 times 7 minus 3 times 2, which gives me just 1, or just K hat. Which means given my original vectors A and B, my cross product is, well, what we just found, -43 I hat plus 13 J hat plus K hat. And that's the process. And again, you should make sure that you go through and take the time and practice, 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 and do a bunch of these cross products because, well, eventually, instead of just doing numerical cross products, we are going to be adding functions to these, which is going to add another layer of, well, difficulty and complexity. So make sure you have the process down and you understand exactly what you're doing now. You should be doing a bunch of cross products through your homework and doing your notes, and make sure that you have the whole thing down perfectly. Now, I do want to mention that there are actually other ways of calculating the determinant. I mean, we already showed that you could just memorize a formula. Your book uses this minor matrix determinant method to find the cross product, so that's what I'm doing as well. But there are actually other methods as well to calculating cross products. And you can absolutely do a quick Google search and find some of those methods, or if you've taken linear algebra, maybe you know a better method yourself. And that's fine. The important part is getting the right answer, not necessarily how we get to the right answer with something like this. And so whatever method you choose to use, just make sure you practice it so thoroughly that you're a master at it and you don't make any mistakes. So let's talk a little bit more about some of these properties. So we mentioned that right-hand rule. And so what happens if I switch the order in which I'm evaluating the cross product, notice that the cross product is going to face in the opposite direction. And again, hold up your right hand and look at that first example with A cross B. A is your index finger, B is your middle finger curling in, and so your thumb sticking straight up, there's your cross product. But again, if I were to switch the order, now B cross A, well, B is your index finger, and A's got to curl inward. And to make that happen and match the picture in the drawing, you're going to have to flip your hand upside down and have your thumb now pointing downward. And this gives us one of our first important properties, that we can't do the cross product in either order. The order is absolutely going to matter when it comes to the cross product. And so we lose one of our, well, kind of nice properties that we had with the dot product. But that's all right. Now the other part of the cross product is the magnitude. So the magnitude of the cross product is going to be equal to the area of that parallelogram spanned by vectors A and B. So again, we're going back to that parallelogram idea from two vectors. So again, let's say I have vectors A and B in space, and then the parallelogram that defines the two of them. We have angle theta in between. Well, it's a parallelogram, and the area of a parallelogram is the base times the height. Well, we know what the base is. The base is my vector A, so the length of the base is the magnitude of A. And now I have to figure out what the height is. Well, to figure out the height, well, looks like I just made a right triangle, which means we're going to use some right triangle trig, SOHCAHTOA. So it looks like the height is my opposite angle. So, and I know my hypotenuse, which is my vector B, so looks like we're going to be using the sine function. So sine of theta is the opposite, which is my height, over the hypotenuse, which in this case is the magnitude of B. And so we can very easily solve for height, multiply both sides by that magnitude of B. So the magnitude of B times sine theta is my height. And I can make that substitution, and there's my formula for the area of the parallelogram spanned by A and B. So these two formulas here, very important, and they're going to show up again. The area of the parallelogram is the magnitude of the cross product, and we can calculate the magnitude of the cross product as the magnitude of A times the magnitude of B times sine theta. All right. Again, I'm putting a box around this because this is going to show up again and again. When we get to integration, it turns out that this formula right there is a very important one that we're going to see again and again. So make a note of it now. So, turns out what we just did is actually considered a theorem. If theta is the angle between vectors A and B, then the magnitude of the cross product is, well, magnitude of A, magnitude of B, sine theta. This also gives us a corollary that says that two vectors are parallel, meaning theta equals 0 or theta equals pi, if and only if the cross product is the 0 vector. So if two vectors are parallel, then their cross product is going to be the 0 vector, which is very useful, and it's actually a very convenient way to, again, determine whether or not two vectors are parallel. It gives us another tool to use in our bag of tricks in case we come up against that sort of question. And again, this is an incredibly powerful idea. And again, it should kind of make sense because if two vectors are parallel, meaning they're facing in the same direction, well then how would I orient that plane in space so that I can get an orthogonal vector from them? Well, you can't, because if the two vectors are parallel, meaning they're in the same direction, then literally every other vector, you come up with infinity many vectors that are perpendicular or orthogonal, because, well, we kind of lose some information about orientation there. So here are all the properties of the cross product. So number one is the one we talked about with that right-hand rule already. And then the rest of these are mostly all just variations on the distributive property. The one I want to take a closer look at, though, is going to be property number 5, because property number 5 combines a dot product and a cross product. And again, the nice part is we can do that in either order, as long as the vectors are all in the same orders. A, B, C, we can do the dot product first or the cross product first. And number 5, property number 5, has a special name called the scalar triple product. And the idea here is that if I'm given 3 vectors in three-dimensional space, A, B, and C, and I put them all in standard position, then they're actually going to form a parallelepiped, which is another word for a three-dimensional parallelogram or a rectangular prism. And so, again, hopefully from the picture, it seems kind of obvious that, again, if I have 2 vectors, in this case B and C, right, they're going to form a parallelogram down there on the bottom. Vector A, well, that'll form another portion of this parallelogram, creating, well, a three-dimensional shape. Now, how would I calculate the volume of this parallelepiped? Well, the nice part is, again, because it's all based on parallelograms, the volume is just going to be the height times the area of the base. Well, we know how to find the area of the base. That's the magnitude of the cross product. So it's the magnitude of the cross product of vectors B and C. Well, then the height is going to be the component of A along the base. And if you remember from our lesson on dot products, to find that component, well, it's the dot product. So the volume is going to be the absolute value of the dot product of A with the cross product of B and C. And again, the nice part about property 5 is that, well, we could actually do it in either order, as long as we keep vectors A, B, and C all together. Another definition, we say vectors are coplanar if they all lie in the same plane. And the nice part is we can actually use the scalar triple product to determine whether these 3 vectors are coplanar. If the 3 vectors are coplanar, well, then the scalar triple product has got to be 0, because that scalar triple product is my volume. So if I end up with 0 for my volume, clearly they must be coplanar, because there is no height. It's just a parallelogram. So example 2, are these 3 vectors coplanar? Now, we could actually go through and do the scalar triple product as written, meaning we could find the cross product of B and C, then dot it with A. But, and again, this might become more obvious as we practice and do more cross products, we can actually do this as just doing the determinant of the 3x3 matrix with each of these vectors as the rows. So basically vector A, B, and C, each vector is its own row, and we're going to do the determinant, doing again the minor matrix decomposition based on this 3x3. And again, remember, because again, when we set it up and we do our scalar triple product, when I start with the first one and I, circle, say, the 2, right? And then I make my minor matrix out of that, well, we're doing the cross product, and then I'm multiplying times 2. I'm doing that multiplication. I'm doing that dot product part actually while I'm figuring out this determinant of my 3x3 matrix. Right? I'm actually still dotting, doing the dot product with my components. So what you should do now is pause this video, and you should absolutely go through and try to calculate this, well, determinant by yourself. See if you remember the process, making sure we alternate our signs, obviously. And hopefully, again, we get it set up like this. Again, pause the video, make sure you get to this step on your own. Once you get to this step, try to finish the problem, right? Actually do each of the 2x2 determinants, and when you're done, you can unpause the video. Remember to alternate the signs, do all the arithmetic, and we should get 0, which means these vectors are coplanar. It means the volume of that parallelepiped would be 0, which means there is no volume, which means they're all in the same plane or they're coplanar. And again, I'm not going through the entire process in this video because that's for you to do. So again, take the time on your own paper, make sure you write out this determinant and make sure you get the same answer as me. If not, see if you can figure out where you went a little bit off. See if you can figure out where your math stopped matching mine. Next definition, and this is going to be a really important one as well throughout the remainder of our course, and that's the normal vector. So the normal vector, which we typically denote with, well, n, right, a vector n, is the vector that is orthogonal to some object in space. So we can be normal to a plane, which again is very much related to how we set up our cross product, but it can also be normal to a curve. And so at some point on my curve, we have a normal vector that's going to be perpendicular at that point, or even on a surface in 3 dimensions. At a point on that surface, there is going to be a normal or orthogonal vector to every point. Now, the normal vector with magnitude 1 is called a unit normal, and we've talked about unit vectors before. And that also means that, again, you might see this definition other places, that the cross product can be defined if the normal vector has a magnitude of 1 as, well, using that magnitude of the cross product times a unit normal will give us, well, again, it's all about magnitude and direction with our vectors. And we'll have the magnitude and the direction, and again, you'll see sometimes the normal vector given like that. All right. Example 3. A plane contains 3 points P, Q, and R, and I want to find a vector that's normal to this plane that contains these 3 points. Well, how would I go about doing that? How would I go about doing that? Well, first, if I want to find a normal vector, and again, the hint is that this entire section has been about cross products, and we know that the cross product will be orthogonal or normal, then I need 2 vectors. So I'm going to have to actually take my points on the plane and find 2 vectors based on those points. Now, those 3 points in space are going to form a triangle, so there's 3 sides to that triangle, and technically you could actually go both directions because direction matters with vectors. So there's 6 different possibilities you could choose, although you got to make sure you don't just choose 2 opposite vectors. But again, we can find any 2 vectors we like. Now, me going through, I'm going to find vector PQ and PR. And again, remember, to find those vectors that connect 2 points, you're just finding the difference between each of their components. All right, the terminal minus the initial. And so I find my 2 vectors. So PQ is the vector 4, 2, 3. PR is the vector 3, 3, 4. And again, go through, pause the video, double check, and make sure you're getting the same thing as I am. Did you get the same thing? Then let's continue. Now we know that the cross product of these 2 vectors has got to also be orthogonal. So now we're going to find the cross product of these 2 vectors. So again, the standard basis on my top row, the first vector in my second row, and the last vector as my bottom row. And now do the cross product. Again, pause the video, do this cross product on your own paper, practice, and then when you're done, unpause the video and check to see if you got the same answer as me. All right, again, that should be what the minor matrix determinants look like. And so the cross product should end up being minus 1 I hat minus 7 j hat plus 6 k hat. And there we go. That's our normal vector. Now note, we could have actually picked different vectors to start with, right? I picked two sides of the triangle. I could have picked the third side of the triangle and done a different combination. And I'm going to still get a normal vector, but it might not actually be the same exact normal vector, because any scalar multiple is also going to be normal. And so if you did choose other sides of the triangle and you find that cross product, even if your answer is different, it should still be a multiple of this normal vector that we found. Now again, typically to find normal vectors, well, our process is always going to be to take the cross product of two vectors we know that lie in the same orientation of a plane. If you don't have those two vectors, then your intermediate goal is going to be to find those two vectors, like we just did in that last example 3. Next up, the standard basis that we've talked about, the I hat, j hat, k hat. Well, again, remember each of those have magnitude 1, and they're all along my coordinate axes. And so it turns out that they are all related to each other through the cross product as well. And again, you can play around with this doing the right hand rule. Actually hold your right hand up in space. And I cross j is going to give me k. J cross k is going to give me I. And k cross I is going to give me j. And again, you should be able to verify that pretty simply just using the right hand rule and, well, holding your hand up in space. The last thing about the cross product is one of its most common applications in terms of physics and engineering, and that is in the calculation of torque. So torque is a twisting force that causes rotation. And again, we typically give torque as a vector tau, the Greek letter tau. And we calculate torque by finding the cross product of the distance vector and your force vector. And so typically we think about this as a wrench. And if you've ever done any mechanical work on cars, you've probably come across, well, everything has a certain number of foot-pounds that we apply torque to. So again, when you put your wheels back on your car, there's a certain torque that they're supposed to be, that each of the lug nuts are supposed to be torqued down to. And again, it's very much related to, and this makes a lot of sense if you've ever actually done mechanical work, it is the cross product of the distance and the force. So you're going to get more torque the further away you are from the nut. So again, if you've ever been a mechanic, breaker bars, or if you want to loosen a bolt, the longer the wrench, the more force you'll be able to apply on that bolt. And then of course, more force if you go straight down from the end of the wrench as well. And we can calculate the magnitude of the torque, well, by using that formula we had before, right? Where the magnitude of torque is going to be the magnitude then of the cross product that defines it, and there's our formula. All right, so that wraps up what we wanted to talk about with the cross product. Again, this is one of those sections where you're going to have to practice quite a bit. Make sure you do all of your homework, and good luck. Email me if you have any questions. Bye.